In this video, we're going to learn how to find a basis of the eigenspace associated to a given eigenvalue. So just a quick reminder, remember that an eigenvector is a vector that simply gets stretched out when we do matrix multiplication. So another way of saying this is that when you multiply it by A, you just get some scalar times your vector back. So if we're handed an eigenvalue lambda and we're trying to find the eigenvectors, we just need to find the vectors that satisfy AX equals lambda x. And the way we do that is similar to when we're finding eigenvalues. We'll rearrange this and factor out. And so we're looking, when does A minus lambda I times x equals 0? And to rephrase this in terms of things we've learned before, this is saying that x is an element of the kernel of A minus lambda I. So if we're trying to find a basis of the eigenspace, we're just trying to find a basis of the kernel of a particular linear transformation. All right, so for this particular problem written in black here, we want to find a basis of the eigenspace associated to eigenvalue -3 for this matrix A. So we're going to try and find the kernel of A minus -3i. So the first thing we'll do is we'll write down A minus -3i, which is the same thing as A plus 3i. So the identity matrix is 1's on the diagonal, so 3 times the identity matrix is 3's on the diagonal and 0's everywhere else. So we'll add a 3 to the first spot. We'll add a 3 in the second spot of the second row. We'll add a 3 to the third spot of the third row. And in the fourth row, we'll add a 3 to the fourth spot. Now, in order to find the kernel, we'll need to do the reduced row echelon form. Which I've gone ahead and typed into a calculator. And we end up with 1, 4, 0, -1, 0, 0, 1, -2, and then 2 rows without a pivot. So now if we look at our reduced matrix here, we see 2 non-pivot columns, so we'll have 2 free variables. So we can, let's say, x2 be A and x4 be B. And now our first row says x1 plus 4x2. Well, x2 is A, so I'll go ahead and write an A there. And then minus x4, which was B, should be equal to 0. Where I said x2 is A. Our second row says x3 minus 2 x4s. x4 was B, should also be 0. So now if we just look at our first and third equation and solve them for x1 and x3, we'll have x1 is -4a plus b, x2 is a, x3 is 2b, and x4 is b. That'll allow us to write down the kernel of a minus -3i. So these are all of our vectors. We said x1 is -4a plus b, x2 is a, x3 is 2b, and x4 is b. And now we simply want to note that this is the span of 2 vectors. From the a's, we have the -4, 1, 0, 0. And from the b's, we have 1, 0, 2, 1. So those 2 vectors are linearly independent. So our set of these 2 vectors, -4, 1, 0, 0, and 1, 0, 2, 1, this set is a basis of the eigenspace. So as I've written that, it's slightly ambiguous because every eigenvalue is going to have their own eigenspace, but in this particular context, we've only talked about one eigenvalue. So it's clear that the eigenspace we're talking about here is associated to this eigenvalue, -3 up there. If whatever you're working on, you're talking about multiple eigenvalues, then you should then say which eigenspace you're talking about down here. But for this context, this is fine.